Hi everyone. Today let's talk about sessions 5.7, the gamma distribution. Gamma distribution is used in such as like actuarial science. Okay, here is the definition. A random variable x has the gamma distribution if it has PDF. Well, yes, it's quite complicated, okay? So we don't use the PDF to calculate the gamma distribution. We also use the CDF to calculate it. Okay, here you see this gamma alpha is a value of the gamma function. So this is the gamma function. And we denote the gamma distribution to be this. So we have two parameters, alpha and beta, and they're both positive. So here are some remarks. Gamma of alpha equals to alpha minus 1 times gamma alpha minus 1 for all the alpha greater than 1. Well, that is because of the integration by parts formula. Alright, so if you can remember integration by parts, integral of u dv is uv minus integral of v du. So here, what we do is we consider this is our u, and then this is our dv. Then du will be derivative of u, which is alpha minus 1 times alpha to the, x to the alpha minus 2. And because dv is e to the minus x, v will be e to the minus x divided by minus 1. It's the same as multiplied by 1. Okay, and then by the integration by parts formula, okay, the integral equals uv, so u v, and so that's here, minus integral of v du, so that's du. Oh, I forgot my dx here. Okay, so that's by the integration by parts. And you can see here when we evaluate from 0 to infinity, when we plug in 0, alpha, so when we plug in x is 0, we get 0. But when x goes to infinity, this is actually looks like x to the alpha minus 1 over e to the x. So when x goes to infinity, you can see the exponential grow faster than the power function. So this guy also goes to 0 as x goes to infinity. So that's why this guy is 0 when we evaluate from 0 to infinity. So the integral becomes minus become plus. So we have plus. We factor out the alpha minus 1. And what's left? Well, you can compare this guy and this guy. What's the difference? Well, it was alpha minus 1, now it's alpha minus 2. So we just subtract 1 from the alpha. So that's why this guy is gamma of alpha minus 1. Okay, so we have shown that gamma alpha equals to alpha minus 1 times gamma alpha minus 1. If alpha is an integer, you can actually keep going. So that's then alpha minus 2 times gamma alpha minus 2. So keep going. We get alpha minus 1, alpha minus 2, until we get to 1. So this is alpha minus 1 factorial. Okay, so if alpha is an integer, then we get this. Here are some facts. If x has the gamma distribution, then the mean equals to alpha times beta, the variance equals to alpha times beta squared. Okay, so here we don't prove it, but if you want to see the proof, feel free to let me know. I'm happy to show you. Okay, so and the formula, you don't need to memorize it. The formula will be given in the exams. Okay, so we just said for gamma, we use the CDF to calculate. Okay, but However, because different alpha and different beta give us a different CDF table, so that's why it's hard to include all the CDF tables for the gamma in the textbook. So that's why I give you this website. This website has generated the gamma table. So let me show you. Okay, so this is the website. It actually has all the different distribution: normal, gamma, exponential, chi, t, chi, f. So those are continuous distribution. And the binomial, negative binomial, geometric, Poisson, hypergeometric, those are discrete distribution. Okay. However, for the continuous distribution, we'll just learn the normal distribution, gamma distribution, exponential, and t distribution. We won't learn chi-square and the f distribution in our course. Okay. So here you can see after you input different alpha and beta values, and then you get a table. Okay, so you can choose to enter the x values and then you get the CDF values, or you can choose to enter the CDF values that give you the x values. Okay, so we'll come back to this website when we go over examples. All right, let's continue. Let's look at example 1. Suppose a survival time x in weeks of a randomly selected male mouse exposed to 240 rads of gamma radiation has a gamma distribution with alpha equals to 8 and beta equals to 15. Part A. Find the expected survival time. Okay, so what does that mean? Well, x is like the survival time. Expected means we're looking for the expected value. That's the expectation. That is the mean. So all of those are different names for the mean. So mean, mu, is E of x. Well, that is alpha times beta. Okay, we use the formula. And then alpha times beta, alpha is 8. Beta is 15. So our answer is 120. So far, so good, everybody? Okay, and then part B. Part B, a mouse survives between 60 and 120 weeks. So between 60 and 120 weeks. But so notice that here, x is the time, right? Survival time. Survival time. Okay, is a continuous random variable. So it has the gamma distribution with alpha is 8. Beta is 15. So this is a continuous random variable. So when we calculate it for continuous random variable, the endpoint doesn't matter. So that's why here I didn't tell you inclusive or exclusive the endpoint, because it does not matter for continuous random variable. Okay? And we don't need continuity correction. Okay, because time is a continuous random variable, so we only use continuity correction when we use the continuous random variable to approximate the discrete random variable. Okay, so what is this? Well, this is the CDF of the final point minus the CDF of the initial point. Okay, so what are those? Well, let's go to our website. So we have alpha equals to 8 and beta equals to 15. Okay, and we're looking for f of 120. So means x is 120. Let's see what's the f. 0.547. So this is 0.547. Subtract, we plug in x is 60. So 60. 0.0511. 0.0511. So we plug this in our calculator. What do we get? We get 0.4959. So this is the probability of a mouse survive between 60 and 120 weeks. Okay, so you can try to pause here and do part C. Are you done? Okay, so a mouse survives at least 30 weeks. At least. So that's greater than or equal to 30 weeks. Okay, so we use CDF to calculate. So greater than equal, we want to change it to less than equal. So the complement of that is less than, but because for continuous random variable, the endpoint does not matter. Less than is the same as less than equal. So this is 1 minus f of 30. What is f of 30? Let's come back to our website. So f 30, we plug in x is 30, and then the CDF is 0.0011. 0.0011. So plug this in our calculator. What do you get? I get 0.9989. So far, so good, everybody? So this is part C. Okay, the probability of a mouse survives at least 30 weeks. Okay, so for given alpha and beta, we go to the website and we plug in the alpha and beta values, and then we can get so the website, it can help us to generate a table like for how small your x be, how big your x be, and the step size. And you can plug in the x values that give you the f CDF, or you can plug in your CDF, let's say 0.875, and then they give you the x values. All right, let's continue. Okay, so that is the gamma distribution. Now, if alpha equals to 1, we actually get an exponential distribution with the lambda equals to 1 over beta. So the exponential distribution is just a special case of the gamma distribution. And why do we want to talk about this special case? Because it has great use. Okay, so this is a special case of the gamma distribution. Okay, so a random variable x has exponential distribution with the parameter lambda if it has the PDF, this guy. Okay. So you can see we plug in alpha to be 1. When we plug in alpha equals to 1, you will see here the gamma is actually 1. Okay? And so we plug in alpha equals 1. This guy is gone. This guy is gone. It's 1. And beta to the 1, right? And then so 1 over beta is lambda. So you have lambda and then e to the minus lambda x. So this is what happened when we plug in alpha equals to 1 and beta equals to 1 over lambda. Okay? So that's why we get the PDF of the exponential distribution. Okay. So, and we denote x has the exponential distribution. Okay, remark, if x has the exponential distribution, then the mean is 1 over lambda, and the variance is 1 over lambda squared. Well, how do we get that? Because remember, it's a special case of gamma distribution. So the mean is alpha times beta. But alpha is 1, beta is 1 over lambda. So that's why we get 1 over lambda. And the variance is alpha times beta squared. And alpha is 1. Beta is 1 over lambda squared. Beta is 1 over lambda. So that's why we get the variance is 1 over lambda squared. Okay. So, what is the main use of the exponential distribution? So actually it's related to the Poisson process. Do you still remember the Poisson process from chapter 4? Okay. So Poisson process, we have alpha is the average number of success per unit of time. So unit of time could be per day, per hour, or per minute. And we let t be the time interval. It could be 2 days or 1 day, etc. Okay, and let x be the number of success in this time interval. Then we know it has the Poisson distribution with the lambda equals to alpha times t. Okay, so Poisson distribution. So, okay, Poisson, the x is like a number of success per period of time, right? So today, let y be the waiting time between successive arrivals. Okay, then it actually has the exponential distribution. Okay, so y has the exponential distribution where my lambda is alpha, which is the number of success per unit of time. Okay, so 1 over lambda is the time between two successive. So the exponential distribution, y, corresponds to the time between two successive success. Okay, so you can see it's like they flip. Okay, if you asked the number of success per unit of time, that's Poisson distribution. If you ask the time between two success, well, that is exponential distribution. And you can see this guy. This guy is a discrete random variable where the exponential distribution is about the time. So it's a continuous random variable. Okay, so for Poisson distribution, lambda is alpha times t. But for exponential distribution, the lambda is just alpha. So usually you will see those two different distributions in the same problem. So you need to identify when do we use the Poisson distribution, when do we use the exponential distribution. Okay, so let's look at this example. Example 2. Okay, on average, 3 trucks arrive per hour. Okay, so what is alpha? Well, alpha is 3, right? So on average, this is the average number of arrivals per hour. The unit of time is hour. Okay, let's look at part A. At most 20 trucks will arrive during an 8-hour day. Well, we are talking about the number of arrivals, right? So this is a Poisson distribution where t equals to 8-hour day, so 8 hour. Well, Poisson distribution, we care about lambda. Lambda is then alpha times t. Alpha is 3, and t is what? 8. So we have 24. So far, so good, everybody? So, and we are looking for at most 20 trucks. So at most, it's like less than equal to 20 trucks. Okay. So what is this? Well, this is exactly the CDF. So this is the CDF of 20 with my lambda is 24. Okay, what is this number? However, our table 2 for the CDF for lambda, CDF for the Poisson distribution, that our lambda is only up to 15. But here we have 24. Wow, that's okay. we use our online stat calculator. Okay, so which is the website I just showed you. Okay, so let's see here. That's the website. So we're looking for Poisson distribution. So that's the Poisson distribution. Okay, and what is our lambda? Our lambda is 24. Okay, and we are looking for the CDF where my x, so k. So we use x for continuous random variable, and for discrete random variable, we usually call it k. So k is 20. Okay, so here it generates the PMF and the CDF, and we are looking for the CDF. So the CDF is 0.2426. So this is 0.2426. Okay, so it because you may notice that the website also gives us PMF, because for discrete distribution, the PMF is the probability at that value. So that's the probability when x equals to 20. Okay, so we have a number there. But for continuous random variable, we don't have the probability at a single point, because the probability at a single point is 0. Okay, so that is part A. How about part B? Okay, so part B, we're looking for the probability of time between successive trucks is less than 5 minutes. Well, that is the time. If the problem is asking the time between successive arrivals, then we use exponential distribution with lambda is alpha. So the lambda is 3. Okay, so kind of we called you, if you remember for Poisson distribution, different parts, if the t is different, then the lambda will change. However, for the exponential distribution, your lambda is always alpha. So in the same problem, lambda is always the same. Okay, it's just the alpha. All right, so for exponential distribution, we're gonna use the PDF to calculate. Okay, but here 5 minutes, our unit is hours. So what is 5 minutes? Okay, we want to get rid of minutes, we want to get hours. Then what's the relationship between hour and minutes? 1 hour is 60 minutes. 5 over 60 is 112. So far, so good. So keep that in mind for exponential distribution. We're going to integrate this PDF. And you can see when x is less than 0, it's just 0. So that's why here we have the integral. So p successive time is less than 5 minutes, which is 1 over 12 hours. And let's start with 0, because when x is less than 0, the PDF is 0. So integral from 0 to 112, and we have lambda e to the minus lambda x. The lambda is 3. Okay, so how do we integrate that? Well, we have e to the negative 3x. And then 3 here, we divide it by negative 3, right? And then we evaluate from 0 to 12. 3 cancel. So we plug in 112 first. So we have minus e to the negative 3 times 112. Minus negative become positive. So we plug in 0. E to the 0 is 1. Oh, so our answer is 1 minus e to the 3 and 12. That's like 1/4. So far, so good, everybody. And so we plug this in our calculator. Okay, we plug this in our calculator. What do we get? So let me see. 1 minus e to the negative 1/4. The answer is 0.221199. Okay, so we round up, so 2212. So far, so good, everybody. So for exponential distribution, we use the PDF to calculate. So we integrate the PDF. All right, so that is part B. How about part C? Time between the successive trucks is at least 45 minutes. So it's still about the time. Then we have the exponential distribution. Okay, and the lambda is the same. Lambda is the alpha, so it's always the same for exponential distribution. So here, at least 45 minutes. So what is 45 minutes? Well, 45 minutes is 45 over 60. The common factor is 15. 45 divided by 15 is 3. 60 divided by 15 is 4. So we are looking for x at least greater or equal to 3 over 4. So far, so good, everybody? All right. So let's calculate. This is the integral 3 over 4 greater or equal, so it goes to infinity, lambda, so 3 e to the minus 3x dx. Okay, so because there is a infinity means we need to replace it by t and let t goes to infinity. This is improper integral, right? We cannot plug in infinity. Infinity is not a number, it's a process. So that's why you let the limits t goes to infinity. Okay, let's integrate it. So we have 3 e to the minus 3x over negative 3. Evaluate from 3 over 4 to t. So 3 cancel. We have limits. T goes to infinity. That is, what is that? Okay, so we plug in t first, so minus e to the negative 3t. Then we plug in 3/4. So minus become plus. E to the negative 3/4. Okay, when t goes to infinity, what is this guy? Well, exponential function looks like that. But when t goes to infinity, minus 3t goes to minus infinity, the exponential term will get to 0. Okay, so the answer is minus negative 9 over 4. Plug this in our calculator. So So everybody try to plug this in your calculator. E to the negative 9 over 4. That is 0.105399. So we round up to 54. Okay. So this is a solution of example 2. So keep in mind, in the same problem, we might see Poisson distribution and exponential distribution. If the problem is asking the number of arrivals per time, a time interval on a time interval, then we have Poisson distribution, and the lambda is alpha times t. Where if the problem asks us to find the time between the successive arrivals, then that is the exponential distribution. And the lambda is alpha, so it's fixed. Okay? Alright, so that is example 2. Let's look at example 3. Suppose the response time x at a certain online computer terminal. The elapsed time between the end of a user's inquiry and the beginning of the system's response to that inquiry has an exponential distribution with expected response time equals to 5 seconds. Part A. What is the probability that the response time is at most 10 seconds? Part B. What is the probability that the response time is between 5 and 10 seconds? Part C, what is the value of x for which the probability of exceeding that value is 1%. Okay, so first of all, what information do we have? Expected response time is 5 seconds. What is the expected value? That is the mean, right? From this sentence, we know the mean is 5 seconds. But what is mean? Do you remember for exponential distribution? You don't need to memorize it, but we have the formula for the mean. Mean is 1 over lambda. So 1 over lambda equals to 5. Then what is lambda? 1 over 5, which is 0.2. Right? So that is lambda. Then let's look at the first one. So what is the probability? So here we know it's exponential distribution, right? It's right here. Okay, and what's the probability that the response time is at most? At most means less than equal to 10 seconds. That's the interval from 0 to 10. Lambda is 0.2 e to the minus lambda 0.2x dx. Okay, let's integrate that. So we integrate that, we have 0.2 e to the minus 0.2x divided by negative 0.2. Well, 0.2 cancel. We plug in 0 to 10. So that means we plug in 10 first. So minus 0.2 times 10. Minus become plus. E to the, we plug in 0. So here we get negative e to the minus 2 plus 1. So plug this in our calculator. What do we get? I get 0.8647. So far so good, everybody? Okay, that's part A. Part B, what is the probability that the response time is between 5 and 10 seconds? So it's asking 5 and 10. And here, the problem doesn't tell us inclusive or exclusive. And we don't need to know that because for continuous random variable, the endpoint does not matter. Okay, so here less than or less than equal is the same thing, same calculation. Okay, so this is the integral from 5 to 10. And then we have the same function. So when we integrate it, it's the same, right? So we have e to the negative 0.2x, plug in 5 and 10. We plug in 10 first. E to the negative 0.2 times 10 is 2. Minus negative become plus. E to the minus 0.2 times 5, that's 1. Okay, put this in our calculator. E to the minus 1, subtract e to the minus 2, we get approximately equals to 0.2325. Do you have the same answer? And then part C, what is the values for x, for which the probability of exceeding that value? So we are looking for the x value such that the probability of x exceeding that value is 1%. 1% is 0.01, right? Wow, what does that mean? Well, we draw the picture. Oh, I forgot to show you what are the picture for the exponential distribution. So here are the graphs. So this graph is on our course website. So here are the graphs for the discrete random variable. Okay, maybe it's good to review with you. So this is the binomial distribution, and this is the CDF for it. You can see the dots is increasing. Okay. And here we have the geometric distribution and the CDF also increasing. And the Poisson distribution, you can see the shape is quite similar to the binomial distribution. And that's right, because we can use Poisson distribution to approximate it. So it's better similar, okay? And the CDF is also increasing. For negative binomial, this is also PMF. I didn't put the CDF graph here. Okay, so the CDF here is missing. I didn't provide that. And for the continuous random variable, we know the PDF. Okay, so the PDF probability density function, this is the probability density function for the uniform distribution. And for the CDF, this is the CDF because this is a constant term. Constant function, integral of constant function is a linear function. So that's why you get a line segment over there. And here we know the normal distribution looks like this shape, right? It's symmetric about the center. And here you can see the CDF is increasing. And here we have the PDF for the exponential distribution is going down. And the CDF is also increasing. Okay, for the gamma distribution, so we have the gamma distribution, and you can see here, so if alpha equals to 1, and then we actually looks like the exponential distribution, and the CDF is also increasing. Okay, so for continuous random variable, we have increasing, but actually the probability for the CDF is non-decreasing. It could stay the same and increase. Okay. All right, so let's come back. Okay, so we have the Poisson distribution. It's like 0 and like that, right? Okay, so it's asking x greater or equal to the small x values. So this is 0.01. So that means probability x less than or equal to small x is 0.99. So this is 0.99, right? So that's the same as saying that integral from 0 to x of our function. So our function is lambda in this case is 0.2, and e to the minus 0.2, let's use y because x is our x value. We want to figure that out. So let's use y to denote our independence variable. Okay, so that is, we integrate it, we get negative e to the negative 0.2 y, and then we evaluate from 0 to x. So we plug in x first, then we plug in 0. So when we plug in 0, minus become plus 1. So that equals 0.99. Well, negative e to the minus 2x equals to 0.99, subtract 1, 0.01. And e to the minus 0.2x equals to 0.1. And we take the natural log on both sides. Negative 0.2x is natural log of 0.01. Finally, what is x? Natural log of 0.01 divided by negative 0.2. And plug this in our calculator. What do we get? Well, this approximately equals to 23.026 seconds. Okay, so sometimes students will do, okay, I don't want to look at this. I can just use this. Okay, if we use that, then we have integral from x to infinity 0.2 e to the minus 0.2 y dy. This is 0.01, sorry. Okay, so that's the area on the right hand side of the x. Okay, so same thing, you can do that. So when you integrate, you get minus e to the point to y, evaluate from x to infinity, but let's don't call it infinity. We call it t, and we let t go to infinity. Because infinity is not a number, we cannot like plot in it. So negative e to the minus 0.2t minus become plus e to the 0.2x. And when t goes to infinity, negative 0.2t goes to minus infinity. So this guy is actually going to 0. So we get minus e to the negative 0.2x equals to 0.01. Well, that's exactly that. So we go down and we will get the same answer. Okay? So that is part C. So here we're giving the probability and we're looking for the x values. So far, so good, everybody. So that finished example 3. All right. So then that is it for chapter 5. Okay. So later on, we will do a chapter 5 review. Bye.